So since Amin is not here, let's wait for 2
Yeah,
minutes.
you can wait. You can, yeah. Sure.
Yeah.
I think they have one of them maybe can contact him.
Yeah, yeah. If possible, one of you. Amin is not here. Let's.
Okay, I'll message you.
There's some chat. Oh, I did it. Okay.
Yeah, I'll record on my end. Okay, let me start before I forget this.
Maybe Amin has not fully recovered yet. I think apparently he took his vaccination.
Oh, okay.
Side effects.
He's saying that he has some connection problems.
Okay.
Okay.
Yeah, maybe you should try. Of course, he won't be able to ask questions then if he has connection problems. Sometimes live stream.
Yeah, the YouTube live stream is usually much easier to connect to than this. But
Already
yeah,
started the live stream.
yeah. So maybe like ask him if possible to try to join. Otherwise, follow the live stream, and maybe we should start because. What do you think, sir?
Yeah, I think so. You could message him.
Yeah.
I'm sorry, I'm saying one of, so I don't have his number. So tell him that, let's see, he's here.
Okay. Yeah.
He's almost here. Yeah, okay.
Yeah, okay. So I'll start now.
Yes, you can.
So yeah, so let me start sharing the screen. Wait a second. Yeah, is my screen visible?
Yes.
Yeah, okay. So did everyone have a chance to go through the code that I know I sent it kind of late, but did anyone go through it, and do you have any questions, in specific questions with respect to that? Or even before that, could you install CUDD? Were you able to, or was there any problem with installing CUDD or anything like that?
No, I installed this already.
Okay.
But I haven't tried it.
Yeah, I mean, so what are you on? So what Ubuntu, which Ubuntu?
20.
Okay.
20.
Okay, so how did you use that PPA, or did you install it from their source?
From the direct link.
Okay.
I've downloaded the tar package and installed.
Okay. So I tried that on a virtual machine for Ubuntu 20.1. The thing is, there it was giving me some link errors, which is why I said that for Ubuntu, like the PPA may have been better. So so yeah, maybe huh? Yeah,
I didn't face any issues in the direct link. Actually, I faced them.
I mean, did you try to compile any code with it yet?
No.
Yeah. So there, if you get some link errors, and if you get some like undefined reference problems, just then maybe try and use the PPS. I've in the README for the tar that I had uploaded to Moodle, there is some instructions for using the PPA. If you want, I can also show it over here. I can start up the virtual machine and show what I had to do for installing this on.
We'll figure it out, I guess.
Yeah.
We'll figure it out ourselves.
Okay, sure. Okay.
If
So
there are some problems, we will message.
Yeah. Okay. So that's one thing. And the other thing that you need is this from the GraphBiz package, which I think is like very common, really easy to install. Just that is fine. Yeah. So let me go into the code. Did you get a chance to read through the code, or should I just go over the code now?
I didn't read any.
Yeah. Okay. So I'll go over the code now.
You want to increase the font size?
Yeah, I will. Once let me
Okay.
CD this and I'll, yeah. Is this font size all right, or bigger or smaller?
Yeah, it's okay.
Okay. Right. So this is basically the file that I shared with you guys. So yeah, so there, let's go over the first simple examples that I had, an example that I had written up. Right. Yeah, I'll increase the font size here as well. Is this okay? The font size?
Yeah, okay.
Okay. Yeah. So, okay, actually here, I think I forgot to remove these few helper functions, but they're not necessary. So I'm just going to make them now. Yeah. So, right. So the CUDT is basically written and used as a C package, which means that the basic structure for your using it is going to always you'll need to basically initialize a manager, and for almost every function you need to just pass that manager in while you're calling the function, right? So the manager is basically what maintains your global state of the CUDT library, like it tracks all the nodes. So sir, I think sir maybe had mentioned last time also that this is done by maintaining two tables, which the details of which we don't need to go to, but that's what basically the manager has, these two tables and so on. And so firstly, you need to initialize this. So that is why CUDT underscore init, right? So you pass a few arguments over here. This is the initial number of variables that you want to put into the manager. So you can pass in 0, and then you can just keep adding variables in, or you can pre-allocate with as many variables as you want. This one is some internal parameters. These all three of them are some internal parameters, and I would recommend that you just keep this one to 0 and use these two macros for this. This is some internal parameters to tune the initial and like the memory allocation and the cache interaction and all of that. And like documentation recommends that you leave it at this unless you really know what you're doing. Yeah, and this is some bound on the memory that you want to pass to CUDT. Again, 0 means unlimited in this case. So I'd recommend that you just keep it to 0. Or if you want to, like if you are on some system where you want to keep some bound, then you can do that as well. This is the bound in bytes, right? So first thing first, variables in CUDT are basically indexed by some integers, right? So you have variable number 0, variable number 1, variable number 2, and so on. So in CUDT, there's like no inherent naming of variables that you can do, right? So variables are just given by integers. And the way, and also let's make a distinction between variables and the BDD for a variable, right? Because the BDD for a variable is actually a BDD node that points to a variable, whereas the actual variable is just some integer that determines at what level you make a decision out of. You can never take a VDD out of a variable, but you can still have BDDs which involve that variable. So that's some distinction. So yeah, so if you want to say get the variable for a particular index I, you use this function UDD BDD ith var, right? So this function will return the ith variable, in this case the 0th variable. But if no such variable exists yet, because right now we don't have any variable in our manager, right? This will create this variable, right? So for example, if I do this, the first time I call this, it will return me the variable number 0. It will create and return me the variable number 0. But then if I do this again, say I call this again with a different name, so a different pointer, and yeah, so if I call this again and say I pass in 1, then again it will create and return 1 again, because 1 was not there before. But if I pass in 1 again, then what happens is it will return the same BDD for this old 1 variable. So in that case, Y and Z will point to the same 1. So yeah. So now, yeah, there is some reference counting that is important when you're using BDDs. We'll come to that. Let's look at a small example, and let's ignore these CUDD ref calls for now. We'll come back to this. Yeah. So we create this variable, or we get the variable at index 0. We store it at X. And we get the variable at index. So BDD new var, actually, what we'll do is basically it will always create a new variable and intend to use. So right now your BDD manager has 1 variable, and the largest index for any variable there is 0, right? So BDD new var will get the next available variables index and create a new variable with that index and return that return a BDD pointed to that, right? So you'll get X pointing to 0 in this case, and in this case the next available variable is 1, so you'll get Y pointing to 1, right? Yeah. Now another thing that we can do is basically we can get reference to the constant 1 node, right? So remember this BDD CUDD package, it stores everything as COBDDs, right? So you actually only have a constant 1 node. There is no constant 0 node. You create the 0 node by basically knotting the 1 node. And but the constant 1 node you can directly get from the manager. So you can basically use this function CUDD_read1 to get the constant node from the manager, 1 node from the manager, right? And then you can construct a BDD out of all of this. So once you have X, Y, and say the 1 node, then what you can do is basically you can use several combination functions. There are combination functions for and, or. In this case, I've used an if then else function to combine these. So this is the BDDITE function. And what this will do is basically this will take in some BDDs and construct a new BDD that represents the if then else function of this, right? So if X, then if X is true, then Y, else take whatever you pass over here. So in this case is 1. So this is basically be if X, then Y, else 1, or we can say else true, right? So this is X_Y1, and this function will create this BDD, it will construct this BDD and return a pointer to the root node there, right? So now we have constructed this, right? But now, like, what do we do with it? Well, I mean, you can do several things with it, but you can keep constructing more BDDs, do some checks. But as the first program, I think makes much more sense to actually write out the BDD to some file. So that's where the dot files. So CUDD actually allows you to dump the BDD into this specific format called, right? So dot is a format you can specify graphs. So it's a text format for specifying graphs with nodes and edges and things like that. Internet connections are bad. Can people still hear me? Hello?
Yeah.
Hello? Yeah, okay. Sorry.
Yeah, I can hear and see your thing.
Okay.
But maybe some people
hello?
Yeah,
Can you
yeah.
hear me?
Yeah, I can hear you.
Yeah, like your voice just lagged. I think it's your connection. I'm not sure.
it was a bit choppy and clanky a brief period, but now it seems okay. Can you speak?
Yeah, could you just repeat what you said like last about the dots thing?
Yeah. So I'll basically dot is this file format for specifying graphs, right? So it's a text-based file format that is designed to be human readable, where you can specify how to draw a certain graph, right? So it's kind of like so you basically in a dot file you basically say that okay, these are my nodes, they'll be labeled by these, and then these are my edges, they're dotted, solid, or dashed. And you can specify a graph in a sort of human readable syntax, and then there are some specific programs that can take this dot file and actually render out a PNG from it. One of them is the graph based dot program. So I can show you a dot file actually. I'll save this and show you a dot file. If you can't hear me or anything, please stop and tell me, okay? Although I don't know if I'll be able to get that as well, but yeah. So yeah, there is this, there are dot files in BDD dots, I think. Okay, I don't think I have any right now. Okay, cool. So I'll show you a dot file once I create them. Let me go over the code. So the point is, this dot file is basically what this UDD dumps the BDD as, right? And then you need to convert that to a PNG and view it. So the first thing that we need to do is to open the file to which we want to dump the dot. And as you see, we are using the C file syntax. So is everyone familiar with this? Otherwise, you can like look into the docs for fopen and things like that. Yeah. So we can't use the C++ ifstream and ofstream classes because CUDD expects this file descriptor to be passed into a function. So we have to use this, and this is not compatible with C++ file IO. So yeah. So then we open this file and we check if we successfully opened it and so on. Yeah. Now there are a few things that we need to initialize before we print out this BDD. First thing is the names of all the functions that we want to print out. So a function is basically anything that has this augmented root node. And in our case, we have three functions. One is for this just the variable x, or three BDDs, let's say. One is just for the variable x, one is just for the variable y, and one is for the variable x underscore y1, right? So we initialize the names of these three functions in an array. We also, okay, so note again that this array is for C style strings, right? So it's an array of C style like const character pointers, right? So it's not std underscore like std string, it's C style strings. So yeah, we need to pass C style strings because CUDD is C library. Yeah, does anyone say?
Could you repeat what you just said?
Yeah. Yeah.
Could you repeat
Hello?
the last sentence that you said? I think your voice broke.
Okay. Yeah, I think yeah, this connection is creating some issues. Okay, so basically what I said was that you need to basically pass in before you like print out the BDDs, you need to prepare the names of the functions that you want to print out. So names of the particular BDDs that you want to print out. So in this case, that will be so we have three BDDs that we want to print out, right? X, Y, and X underscore Y1. So we just name them as X, Y, X underscore Y1 and pack these names into an array. And this is an array of C style strings is basically what I was pointing out. So is this part clear? Do you hear me?
Yes.
Yeah, okay. So similarly, you would want a corresponding array for each name here. You would want a particular like a DD node over here, a pointer to a DD node. So if you note, DD node pointer is basically DD node is basically your BDD node, and a pointer to BDD node is what we carry around to as a reference to our BDD. So you want an array of pointers to your BDD nodes. So corresponding to the names that you have initialized. So in our case, corresponding to X here, we have X, corresponding to Y, we have Y, corresponding to X underscore Y1, we have X underscore Y1, right? Then we want to name the variables. So if you remember, I said that internally CUDD actually doesn't ever carry around variable names, right? Because that's some string and why waste memory space carrying around variable names. Instead, it just use variable indices. But when you're printing out, it makes sense to pass in. Yeah.
Then I have to leave.
Okay.
So
yeah.
You carry on. And
yeah.
Let's see. The only one thing is, I mean, you will be showing them the library of functions that they already have. You know? So
yeah.
Just give a link to that so that there's a whole bunch of functions that they don't need to.
Yeah, I have actually uploaded a link to the BDD manual to the.
Okay.
Yeah.
Okay. That has the list of functions.
Yeah, that has the list of all the functions. Yeah.
Okay. Yeah. Specifically, I'm curious that there's usually functions to do operations on BDD, but there are also functions to get the SAT instance and so on.
Yes. There are those functions as well.
Yeah. Okay.
Yeah, I don't have code. Okay. Yeah. Okay. I have a code for operations on BDDs, which I'll show in a moment. But yeah.
Okay. Carry on. Bye. Enjoy.
Yeah. So yeah. So can anyone tell me what's the time right now? I'm sorry about that. Just so that I can manage accordingly. I can't see the time on my end. I'm sorry. Hello.
Yeah.
7:24. Yeah,
Oh,
that's
thanks.
yeah. You guys go ahead. I mean,
yeah. Okay. All right. So yeah. So basically, now that we have the variable names, the BDDs, and the function names, we can print it out, dump it to the dot file that we had. We will also open the dot file. So yeah, this is the function for dumping to the dot file. It takes in your DD manager, how many DD nodes are there in this array, right? And takes in then you pass in the array of those DD node pointers, these are funcs. Then you pass in the variable names, and there should be as many variables as you have in your DD manager, right? So as many variables as you have initialized, and you need to keep track of that. So in this case, we have two variables, and then you pass in the names of all the BDD nodes that you have passed in, right? So it's only in this dump dot that you actually ever need to pass in names and such. Otherwise, everything is maintained as pointers and indices and such things. And finally, you pass the file that you want to dump it to, right? Then remember to close this file because CUDD won't like close it for you, right? So this code basically will dump this dump all the BDD that is generated to a dot file. It'll also print out some statistics about your CUDD manager. So a few statistics that you can print out is you can print out the number of variables that have been initialized. So that is the read size function, unintuitively. Size here is number of variables. And you can also print out the number of nodes that have been initialized or are active, essentially. And you can see that with the read node count function, right? Yeah, and then finally you would want to quit. So this basically like releases all the memories that CUDD had acquired to do things. Yeah, so let's compile this function. So to compile this function, you just this is C++, and all you need to do is basically just link against CUDD, right? So simple BDD.cp, and then you do LCUDD, and then finally I'll put the output to let's say there's a build folder here, right? Yeah, simple. This font size is there. Yeah, so the compilation is done. Now let's run this, and I have to run this from this. I can't cd into the build folder because I have actually like hard coded these file paths here, and this file path only makes sense from the current CWD that I have. So just take care of this because otherwise you'll not be able to open the dot file for writing when you run these programs. Oh, sorry, simple BDD. Yeah, so it prints out a number of variables and nodes, and if you look into this BDD dots folder, there is now a BDD dot file. So let's see what that file has. Yeah, so you see this is some text description of some graph, right? So yeah, we don't need to go into this at all, like the syntax for the dot file. So I'll close this, but just know that there's some text description of some graph. And what we'll do is instead we'll render this graph. So that you do using the dot program. This is a part of the GraphVis package which you can install on your Ubuntu thing, on Ubuntu machines. And then you pass in the type of output you want, that's capital T PNG. Then you pass in your input file, so BDD dot, and then you pass in your final output file, which in my case is okay. So actually, it's I think better to pass in the output file before the input file, but yeah. So in my case, I want the output to be inside BDD PNGs, and let's say BDD dot PNG, right? And yeah, then the PNG is created, and let's open it up. So you open it up using any image viewer. Yeah, so now we have this BDD. So let me just make this big. Yes. So yeah, So as we saw here, the code here basically did this, right? So it created this X and Y and all of, and those refer to some BDDs corresponding to the variables X and Y. So here we have two variables. We have variable X, we have variable Y, and the function X and function Y, right? So the function X basically just decides based on the variable X. If variable X is 2, it goes to 1. Otherwise, it goes to 0, right? So the dotted edge here, this is a dotted edge and this is a dashed edge. So can everyone see the difference between a dotted and a dashed edge here?
Yes.
Like, yeah.
Yes.
Okay. So the dotted edge is the complemented 0 bar, and a dashed edge is a normal 0 bar, right? So basic function is if X is true, then you go to 1. Otherwise, you do the complement of 1. So you go to 0. Similarly, if Y go to 1, otherwise you go to the complement of 1, right? And X underscore Y1, what this does is basically this is if X, then Y, else 0, right? So that was what our function was. So else true, sorry. So here we have the function, right? So and we created them using the BDDITE. So this is the operation that we're doing on the BDDs. Right? So you can, as I said, you can do several such operations on, as I said, you can do several such operations on BDDs, and we'll see some more of them. But for a comprehensive list, refer to the manual that I have posted in Moodle. And here, if X, then Y, else 1 is what we're doing. So let's confirm that that's what's happening. Yeah. So if X is true, then you go to this node. Otherwise, you take the dashed edge to 1, right? So dashed edge means not complemented. So if X is false, then we are just saying true. So that part is true. So the else part is true. So then we wanted to say Y. So we go into this node. And again, if Y is true, then we go to 1. Otherwise, we go to 0, right? So then Y is also true. In fact, this node is the same as just Y. So this makes sense. Also note that here, when we had run this program, it said this, right? So it says 2 variables and 4 nodes, correct? And also, while drawing this program, it shows that this particular node is being shared. So there are no 2 copies of this Y node doing the same thing, like it is in the same Y function, right? It is actually the Y function is a part of our if then else function, is actually being shared with the actual Y function that we have here, right? And the 4 nodes that we're counting over here, that this being counted over here, is basically this one, this one, this one, and the constant 1 node. So the constant 1 node is always counted. And then you have these nodes. The augmented root node BDD does not count because internally it actually doesn't need to store these augmented root nodes. It somehow optimizes that out. But yeah, so the nodes that you have, the 4 nodes that you have in this case is 1, 2, 3, 4. If you hadn't shared this node, we would have had a 5th node here representing Y, and you wouldn't have this edge and this edge coming to the same node, right? But we actually see that CUDD is intelligently sharing the nodes, and that is the important takeaway here. Does everyone understand the shading? Yeah.
One question.
Yeah.
In X underscore Y1, that is representing if X then Y, right?
Yeah.
If that is the case, why aren't we sharing the X node?
Because the X node is this X node. This does not represent the same function as the function X, right? This is a function which says that if X is true, then true, else false, right? So this is basically so I don't know if I'll be able to write on this. Let's see. Can you see this?
Yes.
Okay. Right. So this one.
Actually no, I can't see. I mean, I'm seeing
it's
something
pretty blurry.
Okay. This doesn't work so exactly. Yeah, it's pretty blurry as well now. Can't seem to stop the annotate. Okay. This was a mistake. Well, I'll stop the share and start again. Sorry.
Never mind. It's not that important.
No. Let me this is fairly important. This question that you asked is an important question. So I'll just go to some new thing. I'll create a general PP and let's. So yeah, so we have this sort of a structure, right? So, okay. So essentially we have this node here and this node, right? So what I'm saying is basically this node, the function for this node is fx equals x, right? And what is the function for this node? The function for this node is this function, right? If x then y else true. So these two nodes represent two different functions, correct?
Yes.
Right. So you can't share them. So you can only share them if they have the same function. If they represent the same function, then for all intents and purposes, they'll like all their outputs will be isomorphic. So they'll represent isomorphic graphs, right? So you can share them if and only if they have the shape function, which is equivalent to like the graphs of them will be isomorphic, correct? So since they represent two different functions, you can't share them, because if you did share them, for example, what would happen was this edge would go to the same node and this edge would go to the same node, and you would have x and x underscore y1 would become the same, right? And that doesn't seem right, correct?
Right.
Yeah. So these two are different functions, so you cannot share them. So it's not like you're going to share for each variable. So then you'd only have one node at each level of the variable, right? And that doesn't make sense. Like then you could only have linearly many nodes in your variables, and then how do you even do SAT in linear time? That doesn't make sense, right? Yeah. So you only share if there are same functions, and this UDT just draws them at the same level because it's the same variable. But in essence, this is not related to this function at all, like in any way. But we have asked UDT to draw them together in one diagram, so it just obliges and does that, right? So okay, so is this diagram clear? Any more questions here as to what's happening in this particular program, or any questions regarding the calls that we're doing, some of the functions, arguments, anything?
Also, just wanted to confirm, you probably said this already. This is a COBDD, right? So the
This is a
dashed
COBDD.
edges are complemented.
Yeah, the dotted edges are complemented, the dashed edges is solid, like not uncomplemented, right?
Okay.
Yeah. So solid is always the true edge, dotted is false and complemented, dashed is false and uncomplemented, correct? So the closer it is to solid, the more true it is. So solid is completely true. Dashed, I remember it like this basically. Dashed is false, but it's still not complemented. It's not that false, and dotted is complemented and false. So it's
okay.
yeah. I mean, yeah, it's a mnemoic, I think. Okay, so is this any more questions here? Should we move on to the next code? Is this fine, everyone? Yes.
Yeah.
Okay.
Yeah, yes.
Okay, so let me move on to the next one. So yeah, the next code that we have is so again, if you do an LS here, this is so yeah, we're doing a SAT check over here, right? So now I won't go over each one of these functions in too much detail. So there's still these ref functions, which I'll talk about in a moment. That is a little important. So I'll want to go over this function that does some more complicated operations with CUDD. And I also want to introduce this particular style. So what I'll always have from henceforth is, so okay, let me just actually show utils.hpp parallelly. So yeah, so this utils function actually just, so you saw that at the end, we're doing two things, right? We were dumping to a dot file, and we're also printing some statistics, right? So from now on, we'll be doing this like several times in a program. So it makes sense for us to just write a function which does that. And this function is just like fairly thin wrapper around dump dot. All that it does is that it manages your file opening and file closing. And instead of taking these C-style arrays, it will take vectors containing C-style strings for your DD names of your nodes and your BDDs, and it will also contain take a vector for your BDD nodes, right? So this is just a wrapper around this UDD dump dot that I've written, and this is in utils.hpp. Similarly, we have a print stat function, which just basically is just this line that we had. This line is just being so not this one. Sorry, this line. This is just been copied over there, right? So you don't need to really worry about what this is doing. And so here at the beginning, like what we'll always do is basically we'll have these vectors. So everybody is familiar with C++, right? So vectors and all of this are familiar things, right? Yes or no?
Yeah.
I know C, but I think I know what a vector is.
Yeah. So think vector as arrays, but you have some good functions to push things into the array and pop things on the array. You can do inserts and deletes very easily. So it's like it's like a array with additional insert and delete functions. Correct?
Okay.
Yeah, that's all you need to do. And I mean, this is just some demo code, and you'll probably all organize this very differently and much more efficiently, hopefully, depending upon your specific use cases and such. So yeah, what I'm saying, all I'm saying is basically I'm going to keep track of all the functions that I have and their names and also all the variable names in these 3 arrays, right? Whenever I create a new variable or a new function, I'll add the names and the BDDs to this these 3 arrays. So it's just so that I don't have to create a list at the end like this and remember to add everything at the end. Okay, so that's all I'm saying. Yeah, so again we initialize this CUDD, and this time let's initialize it with 2 variables here already, right? So then when we take x and y using the ith var, this will not create any new variables, right? So again, so we'll talk about the reference counting, and yeah, again, and we do this thing to like add the things to the array, which you can ignore right now. So you can ignore all of this. All it's doing is some reference counting, which we'll explain, and this is just adding into the arrays of names, right? Now what we do is let's construct xy. So just as a like heads up, the function that we're constructing here is xy and like x and y and not x plus not y. So that's unsat, and we'll show that using BDDs, right? So let's construct xy over here. So what you need to do to construct xy is you do need to do some operation on your BDD x and BDD y, and the operation is AND. So that is the function CUDD BDD AND. It takes in your manager. It takes in the two things that you want to AND, and it will return a node to a new variable that contains the AND of these 2 things. And again, you need to reference this and add it to your list of names, right? Similarly, let's construct not x, not y, and this is using CUDD not. Interestingly, CUDD not does not need your manager. All CUDD not needs is just your BDD node, and it will just return the not of the BDD node. And if I have some time, then I like after I've talked about like all of the other things, I can go into some of the interesting reasons why this is like CUDD not does not need the manager. This is some interesting optimization that they have done. But yeah, but for now, let's just remember that the manager is not necessary here. And in any case, when you will be coding initially, it's a good idea to have the docs open next to you, right? So yeah, so you have CUDD not, which will basically create the not of x and not of y, and we again add them. This time the names of this will be not x and not y. So we are basically, so these line, what it does is just that it will add nx to your list of functions, and it will add the corresponding not x name for that, right? And so on. Now let's construct not x plus not y. So nx p and y, and that is again we are using another operator, and this time we need an OR operator, right? So it's exactly the similar syntax and similar signature as the AND operator. In fact, the signature is exactly the same. It's just that the name is now OR, right? And we add it to, like, we add the nx and ny and get a new node, or it may not be a new node, but we get a reference to a node pointing, representing the function nx or ny, and this is the nx p and y, right? And we add it again. Finally, let's construct the final function. The final function, if you remembered, it was x and y and not x plus not y in brackets, right? So this is the function that we want to construct, correct? Can anyone see this function? Yeah? No?
Yes.
Am I audible? Yeah, okay. Yeah, so what you want to do is basically just an AND of nx, p, and y, and ny, right? Again, the AND syntax is just the same, and let's call this f this time, and let's push back f, and this time we just, in the name, we put in what the function is, right? Right. Now, what we want to do is a stat check, correct? So using CUDD, the way you do, or using any BDD library for all that, the way you do a stat check is that you basically construct the function you want to check for sat, and then you just check whether that function is equal to the 0 function or not, right? Because if your function is unsat, then it should be equal to 0 function. And if your function is not equal to 0 function, then we have a guarantee that it's sat, right? Because otherwise it would. Now, if we know that correct BDD implementation will have one and exactly one node for function. Checking whether your given function f is equal to the zero function or not is equivalent to just constructing the zero function and checking whether the two nodes are the same nodes or not, correct? And this f here, in terms of actual code, what is this f? What is the type of this f? This f is a pointer to a DD node, right? So it's a pointer to your root node for function. Think of your augmented root node that you're carrying around, right? So if you have, like, say, two pointers, say one is this for your f, and say you've also somehow constructed this other pointer to the zero node, right? So this basically augmented root representing the zero function, then these two should be the same, correct? So when I say, so okay, so essentially what these pointers are, okay, it's probably not a good idea to say that this is a pointer to the augmented root node. So if you go back to this particular image that we have, so you see that there are three augmented root nodes over here, right? So we had three DD node pointers over here as well, right? So if we go back to this code here, we had three DD node pointers. We had the DD node pointer x and the y, and x underscore y1, right? So the ways UDD basically, so what are these pointers pointing to? If we ask, these are essentially pointing to these nodes. So x would point to this node, y would point to the root decision node for that particular function, and x underscore y1 will also point to the root decision node for the particular function. But CUDD also basically, inside the pointer, it basically sets the most significant bit to 1 if any of these lines are dashed or complemented, right? So this is basically some pointer with some extra information added to it, which basically says that, okay, I'm pointing to the root node, or I'm pointing to the root node with a complement. So essentially, you can imagine the pointer as encapsulating this edge, right? So this edge is what the pointer is in some sense. And these are your values. Yeah.
Are you actually like pointing towards an edge? Because I cannot see anything like that.
Oh.
Can you hear me?
Can you not?
Hello?
Can see the hello? See the image? Can you see the picture?
I can see the
hello?
image, but I cannot see any pointers.
Okay. So okay, my mouse pointer is on. So the edge I'm talking about is the edge from the boxed edges in the top, the x, y, and x underscore y1 to the root decision node. So from x to ox9, from y to oxa, and from y x underscore y1 to oxp. These three edges I'm talking about, right? So your DD node pointer, this is basically, in some sense, these edges are being captured by this pointer. So this pointer basically points to your, so for example, x, DD node pointer x points to ox9, but also captures the information that this is a solid edge, like this is a solid pointer. So if you had x bar, you would have, say, x bar stored in nx, which we'll see, that will be a dotted edge, but that will also point to the ox9. So that will also be a pointer to ox9, but with some additional information that you're pointing to a dotted edge, through a dotted edge, right? So that's what I want to, like, that's what I mean when I say that these pointers are these edges. So the point here is that if you have, so is this okay? So let me just say that. So if you have two pointers pointing to the same sort of root decision node via the same kind of edge, that is equivalent to the fact that these two pointers are talking about the same function, right? And in BDD basically makes sure that in that case, those two pointers will point to the same thing. So that they'll be equal as pointers, right? So does this make sense?
Yeah.
Hello?
Yes.
Yeah. Okay. So essentially what that boils down to is that to check whether two BDDs are same or not, once you have this particular representation, these DD node pointers, all you need to do is to check the equality of those pointers, which is, kind of surprising, but like that the fact that there's no equals function or anything like that, but there isn't. You just need to check whether the pointers is 0 or not. So, okay, so let's see how we are constructing this 0 function. And there is a function to do that. It's called read logic 0. So this is basically just a shorthand for, we saw the read 1, and this function is basically just some shorthand for read 1 and then complement it, right? So that's the read logic 0, but the shorthand is probably more optimized than calling the read 1 and then calling not on that. So we're going to use that. There is also this other function called CUDD read 0, which I've talked about in the comments. That is different. So actually this CUDD package does not only deal with BDDs. There are also other things called ZDDs and ADDs and things like that, which the CUDD package also supports. So there are some functions that you'll see in the docs which pertain to these, and the read 0 is a function that pertains to ADDs. So if you read a 0, it will return a 0 or quote unquote a 0, but it will not be your 0 that you want to work in some other 0. If you try to do operations with that, you'll end up with undefined behavior. So you want to always make sure that you use this read logic 0. And as a general rule, before you use any function, just go through the docs and see that, make sure that it's talking about BDDs and not ADDs or ZDDs or anything like that, right? So yeah, we read this 0 function. And then here what we do is we check if f and 0 as pointers are equals, right? So this is all that we need to do a SAT check. All the heavy lifting has already been done when we are creating this function f, right? And if this function was unsat, the f is already just the same as the 0 function. So all that we need to do a SAT check is just to compare these pointers. And if they're equal, then f is a 0 function, so it's unsat. Otherwise, it's sat, right? Right. So we have some fancy print statement for that. And let's compile and run this code and see what it prints out up until this point before we move on to the other part of the code. So again, all you need to do to compile is link up the, all special thing that you need to do to compile is just link up this LCUDD library. For C, you actually also need to link up the math library. Just keep that in mind. I've written that in the README, but yeah. So for C, you also need the math library. Because this UDT package has references to the math library, which will throw a link later for C. Yeah, I think G++ automatically does linking to the math library for C++, so you don't do that. Yeah, so now let's run this build stat check. Yeah, so let's look at the first lines. We'll come to the second line. So the first line says that first line is this line that we have. And for people who are familiar with C, this std.cr is just some fancy print statement. So if you're not familiar with the cout syntax, don't worry about it. All we're doing is just printing this, then printing the result of this, and then printing a new line character. Right? Okay. So yeah, so this line is saying that x and this x y and not x plus not y is unsat, which is what we would expect. Right. So any questions up until this point? Yes, no? No questions? Yeah, go on. Hello? Hello, am I audible?
Hello? Yeah.
Yeah, go on.
Yeah. No, I just said I had no questions.
Oh, okay. Okay, I see. Yeah, I think the connection is, I don't know how I don't have any better connection on my end as well.
Yeah, sometimes it might be my connection also,
I mean, yeah, it might be anyone's connection, but what can we do is what I'm saying. Yeah, so okay, so if there are no questions, now what we'll do is, as this print line is teased, is that we'll basically construct this function and we'll do an existential abstraction on it. So everyone knows what is, okay, I mean, of course you don't know what an existential abstraction is. This definitely did cover it already. So we'll do an existential abstraction on this function on the variable x and z. And so can everyone see this function, or is this font too small? Yes, no, quickly.
Yeah, I can see.
Okay. So what we do here is basically we construct this function z and not x plus not y, and then we eliminate x and z via an existential abstraction. So what that will leave you with, if you check this, is just a 1, right? Because when you eliminate z, you'll get 0 plus not x plus not y, right? So you just get back not x plus not y. And then when you eliminate x, you get 0 plus not x plus not y. So you say 0 plus not y plus 1 plus not y. So what you get back is a 1, right? So you can check is that this function, after this existential elimination, that is going to be just the one function. So in some sense, it's valid, right? So that's what we check now. So let's firstly construct this function, and the first thing we need to do for that is get a new variable z. So we again we had 0 and 1 for x and y. So let's make z 2, and yeah, we do all the bookkeeping that we need to do for new variables. And then let's say that g is basically going to be what our new function, right? It's going to be z and not x plus not y. That's what g is going to be. So to do that, we and not x plus not y and z, and again we do all the bookkeeping. Now to perform an existential abstraction on g, we need to pass in a set of variables, right? And CUDD has this special way of representing set of variables, which is that it expects you to pass in all the a BDD pointing to the end of all the variables you want to eliminate. So whenever any function inside CUDD, whenever it looks for a set of variables, it will ask you to pass in what this documentation calls is a cube, right? And what that refers to is, I think cube is a standard terminology, but I've seen it very rarely. But what that basically refers to is your AND of variables, where each variable can be either uncomplemented or complemented, right? So basically, if you in CNF formulas, if your clauses are x or not y or z, in DNF formulas, your cubes would be x and not y and z and so on, right? So when you do an existential abstraction, you need to pass in a set of variables, and what CUDD expects you to pass that set of variables as is this cube structure. So it expects you to pass in AND of all the variables, right? So if you say you want to do an existential abstraction on ABC, CUDD would expect you to pass in a BDD that represents A and B and C, right? So in this case, what we want to eliminate over is x and z, right? So we need to pass in x and z as the cube that we want to pass into the existential abstraction function, right? Okay. So with that in mind, I've written this entire thing in one line. I hope this is not too I think it's still fine. So the function that you actually want to do is BDD exist abstract, which is, a fairly nice intuitive name. And then you want to pass in the manager. Firstly, next thing you want to pass is the function that you actually want to abstract. In this case, this is g, which is in our case z and not x plus not y. And then you want to pass in the cube representing all your variables that you want to abstract out. So in our case, that is x and z. So what we do is we directly make a call to CUDD BDD and we and x and z, right? So we get x and z appointed to a BDD representing x and z over here. And we pass that directly to the existential abstraction. And that will return a pointer pointing to the exists xyg function, right? So is this clear? Hello?
Yes.
Yeah. Okay. So again, we do some bookkeeping, and again, we do the same print, which is we're going to see that if this is equal to 1 or not, which is again done in the same way, right? We get the node representing the one function, which is done by the read one, correct? And then if it is true, then we say it's valid. If it's false, we say it's invalid, and so on. And we dump the dot. So we had kept track of all the functions names and variable names, and we dump it to this particular dot file so that we can read it later on. So we've already run the code, which means this dot file should have been saved. And I have this shell script for quickly converting all the dots to PNG. So I'll run that. So yeah, and now let's see this dot file. So BDD sat valid dot.png, right? Okay, so this is a huge file. Let's look at this. So this is basically printing out in the same file all your functions that you have, right? And again, you'll be able to see a ton of sharing here. So again, you have X, and this is there, and you have Y, and again you have not X plus not Y. So not X plus not Y would basically, so you see a dotted edge to a function here, right? So this basically is XY, right? Because the not of X, not X plus not Y is XY. So the moment we had already constructed XY, we already had the not of not X plus not Y. So when we are creating this not X plus not Y, this is basically where that dotted pointer would have gone to. Similarly, we are not X, not Y going to here. Okay, sorry, I forgot that you can't see my mouse pointer, but yeah, so you have edges from not X and not Y to OXA and OXB, and XY goes to OXC, and then there's a dotted complemented edge from not X plus not Y to OXC. If you see your F, XY not X plus not Y, you see that that's just a direct complemented edge to 1. There's no node other than just this 1 that is representing this function. So that basically says that immediately when you have constructed F, you're already, you know that it's just strictly the constant 0 function. And right next to the F, you see that there's a 0, which is also just a dotted edge to your constant 1 node, right? So as you can see that these are basically just both F and 0 are dotted pointers to the same node. So as pointers, they're going to be equal. Now, similarly, we have this Z. We are introducing this new variable Z, and now we have G, which is again Z and not X plus not Y. So this is also being a completed pointer to OXF, and you can go over this and see that that's correct. And then when again you see that you do EXG, that's a solid pointer to just one EXZG, right? So that's just a solid pointer. And if you have not shown the one function here like the 0 function, but you can imagine that the one function will just be a solid pointer to your constant node 1. Right? So any questions with this particular code? And what's the time? Oh, Acha, okay. How long can you guys do? Can you guys do a half an hour more? Yes, no?
Yeah, I mean, you guys should be think, because they also have a class at 3:30. You have to go back, and then I think half an hour. You started at 11:05, so half an hour should be at most, is what I think, and let them.
I'll definitely not push it more than half an hour. Just if half an hour is available for you guys, then say. Otherwise, yeah.
Yeah,
I'm okay with half an hour.
So Amin and Ratnakar is okay. What about Paramalay? If you're not okay, yeah. Hello.
Paramalay is watching
the live stream.
Oh, okay.
What?
I sorry, I didn't see when he dropped off. Paramalay is on the live stream. He has some connection issues. Okay. So I'll continue for half an hour more, and if it's on the live stream, then if he can't, then hopefully, I think he'll have to just check it later on. Sorry. So okay, so that's okay, right, sir?
Yeah, I think so.
Yeah, okay, yeah, right. So let me go to the next code, which is this ref count. So this basically just talks about the reference counting memory management that CUDD does. It's somewhat important, I feel like, to understand this, especially if you're working with CUDD at a C level, which you'll have to do even if you write code in C++. So right, so this reference counting business is basically this. CUDD has its own internal garbage collector, which kicks in every now and then, and it will delete all the unused nodes. But how does it sort of know which nodes is unused, right? So that it knows by basically keeping a count of the references to all of the nodes, right? So whenever a new node is created, and say, let's get this old image that we had up again. So whenever a new node is created, or for any node, let's say the OXE node, right? So initially when it will be created, it will have no references to it. So the reference count will be 0. But then, the OXF node was supposed to say created after this, in whatever order inside CUDD. And CUDD adds the reference from OXF to OXE to the reference count of OXE. So OXE now has one reference count, which means that in the garbage collection cycle, CUDD will not just delete the OXE node, and that will not lead to dangling pointers or anything like that, right? So essentially, CUDD maintains these reference counts, and and basically in that sense, CUDD will track all the internal references from each node to each one and maintain this reference count. And it'll, in a garbage collection cycle, it'll only delete a node if the reference count of that node goes to 0. But notice there are these two kinds of references here we can think of, right? So one reference is from a parent node to the children node. So let's call them internal references for CUDD. So that will be, suppose, the solid edge from OXF to OXC or the dotted edge from OXF to OXD, right? But there's also these other edges, which is basically our DD manager pointers, right? So the edge from, say, Z to OXD, the solid edge from Z to OXD, or the dotted edge from G to OXF. So these are basically, these edges are being represented, these references are being represented by pointers that is external to CUDD. These are pointers that we hold. CUDD doesn't hold them, right? So CUDD expects us to explicitly and manually do reference counts with respect to these pointers. So whenever we actually get a pointer to this OXF node as the G, CUDD expects us to increase the reference count of the OXF node because we are holding a pointer to it, right? Because you can imagine when the OXF node is initially created and returned to us, it actually has a reference count of 0. So if you go back to this previous function where we are where we are using the G, right? So when we define this G here, so when this G is returned from the CUDD BDD AND, it actually has a reference count of 0, right? Because it doesn't have any parents internally. But we have pointed to this. So we have this edge, this dotted edge from G to OXF that we saw, right? And so let me, okay, fine. Yeah. So, and what we have is that because we have this dotted edge from G to OXF, if we don't actually increment the reference counter of this OXF manually to 1, eventually OXF will get just deleted, and then this DD node pointer G will become a dangling pointer, right? So we need to increase the references. So this is why this CUDD ref thing is there, and you'll notice that I've put CUDD ref every time I've gotten a pointer that I want to keep around. So that's why you need to put in this CUDD ref. And reversely, if you have some pointer that is temporary and you're not keeping that around, you can go away, you can sort of explicitly tell CUDD that this is a temporary by not referencing it. So that's what I've done here, for example, right? So this function will return some pointer, and that will be some dotted or solid edge to some node in my BDT, right? But I'm saying that I don't need this. I don't need to keep this around at all. And that's why I don't reference this. And that means that in the next garbage collection cycle, this will actually get deleted. And if you actually see the statistics that I didn't print stats here, but if you had printed the stats here, you'd see that the nodes with respect to the actual AND, there has to be some AND node created for this cube somewhere, but that will not be there because I've not kept a pointer around to this, and that will get deleted. So you need to get add the references to each pointer that you keep around, right? So whenever you get a pointer to any node, that is basically either a dotted or a solid edge to that node, and you need to call this CUDD ref to increase the reference of the node that you got so that the node doesn't get deleted. So let's go to the ref counts code, and let's close this one. Right. So so again we have initialized it with 2 variables, and we get the variable number 0 and variable number 1, and you see that immediately we are referencing these, right? Because variable 0 and variable 1 in this case, sorry, variable x0 and y0 in our case will point to some BDD node, but the fact that we are pointing to this BDD node, this reference has not been counted for this node yet, right? So we immediately increment the reference of these, right, before we do any other CUDD calls. Right. And in fact, even safer and saner way to do it would be this, right? Yeah. But in my experience, this getting a new variable usually doesn't trigger a garbage collection, but yeah. So yeah. So now let's construct some functions out of x0 and y0, and let's see what happens, right? So now we construct this function x y0, right, which is the XOR of not of the XOR of the x0 and y0, right? So again, notice that here also we are doing two things, right? We're calling this operator BDD XOR. So right now we have seen AND, OR, NOT, and this one is XOR. We've also seen the ITE. There are a few more operators, and again, I would ask you to look into the docs for a comprehensive list. So yeah, so this BDD XOR, what will take is the manager X0 and Y0 will return the XOR of this. So we want to say XY0 is going to be X equals, or X is equivalent to X0 is equivalent to Y0, right? So that's the NOT of the XOR. And so that's how we do this. And notice that this will return some temporary pointer, right? And again, we are not actually referencing this pointer. So we are, by doing that, we are implicitly telling BDD that, okay, it's okay for you to not count that as a reference to some node, but this final XY0 pointer that we get, right, that we're immediately referencing. We want to keep this one around. So whichever node this points to, we want to keep it around, but whichever node this points to, it's okay for you to delete that as long as other references are not there, right? So yeah, so we don't reference that. So yeah, so now we have referenced this XY0 and we do some bookkeeping with respect to that. And at this point, this code will dump this dot as this equiv 0 dot dot, right? And it will say that the first equivalence is constructed and print out some statistics. So let's compile this code and see what the output is up until this point. So okay, let me just edit this one actually. Ref counts. What's my time? 10 minutes is already past. Going to be a little fast. Yeah, and let's run this. Oops. Yeah, so there's a bunch of print statements here, but okay. So there's firstly, let's look at this initializing CUDD, and this initializing. Okay, so does everyone remember the print stats function? If you're not, this is just what it's doing, right? It's just printing out the number of variables and nodes. Yeah, so this is just after the init. So if you remember, we're initted with two variables, right? And this is what right after that, when we print out the statistic, that's what it says, that there are two variables in our BDD table, like in our BDD manager, and there's one node. This one node is basically just a reference to your single constant node that you have, the constant one node, right? Now, after we have created X0, Y0, and XY0, then when we are printing the statistics, that's at this first equivalence constructed after this print statement. So after the first equivalence constructed print statement, we notice that there's still two variables, right? Because we had already allocated two variables when we take the variable 0 and 1 out. We're not creating any new variables. But there are now 4 nodes. So what 4 nodes are these? So for that, let's look at the dot file, the dot output dump, right? So yeah, so again, I'll run this script. Yeah, now there are a bunch of dot files, and let's say PNG is 1, right? Yeah. So is this visible? This in the upper left right corner? Yes, no?
Yes.
Okay. So yeah, so these 4 nodes are just, you have your node for X0, Y0 that is also being shared with the XY0 function, and you have the actual node for XY0, right? And the 4th node is your constant node. So these are your 4 nodes, and all of them are here. So all of this reference and this reference and this reference has been counted. Nothing has been deleted yet, right? And that's why we needed these reference counts. So let me go over so what we do next is, again, we create 2 more variables. So I'm going to go over this bit fast, and I've used 2 different ways to create the variables. I can either explicitly ask for the variable at level 2. I had variable at level 0 and 1, which is X0 and Y0. And I can explicitly ask for the variable at level 2, or I can explicitly ask it to create a new variable. So the first time I ask it, will return the variable 2, and now we have 0, 1, and 2. So when I say create new variable, it will give me the variable 3, right? And we put it in X1, Y1, and we reference them. Very importantly, we reference them. And similarly, we construct again X1 equivalent to Y1. Again, we don't keep a reference to the intermediate XOR pointer that we get, but we do reference the final pointer that we get, right? And if you notice here also, we don't have any extra count or any extra node from the intermediate XOR pointer, right? So that means that reference is not being counted, and CUDD has deleted that. or not kept that around, let's say. And again, we dump the dots into this second file here, 2eqv1.dot, and we see that second equivalence is constructed. So let's see what this. So okay, before we do that, let's see how many. So guess how much do you think? How many nodes do you think will be there after the second equivalence? Or I think you'll probably be able to see right now itself. Any guesses? Before I show the dot file and the output. Okay, fine. So let's see. So let's look at the output itself. So after the second equivalence is constructed, we now have 7 nodes. So does anyone have any guesses as to what 7 nodes these are? So I mean, we know that these 4 nodes should not have been deleted, and let's assume that. So what 3 new nodes would have been created? So you see, the second equivalence is basically just the same as this first one, right? So you'll again, we had this for x0 and y0. So you'll again have the same set of 3 nodes like these for x1 and y1, right? So you'll have 3 nodes coming from x1 not and y0, 3 nodes coming from x1 and y1, and then 1 node. So that's what we'll see. So if I close this and actually let's open all of them. Yeah, and so if you see the second one, so again, you see that there are 3 nodes that we had previously from x0 and y0. So these are OXA, OXB, OXC that we had previously, the same 3 nodes. And now we have OXE, F, and OX10, right? OX10. So these are just the 3 nodes that we have. And as you can see, there are no sharing between these 3 nodes at all, because these are just x0 equal to y0 and x1 equal to y1, 2 completely independent functions. And we have 3 nodes for this one, 3 nodes for this one, right? So a total of 1, 2, 3, 4, 5, 6, and 7 nodes, correct? So that's what we say over here as well. Once the second equivalence is constructed, we now have 7 nodes. Now the next thing that we do is we take an AND of these two. So we say x0 equivalent to y0 and x1 equivalent to y1. So if you remember, this was the example that we had running during the theoretical classes. And so I'm just constructing the same example over here. So once we're constructing this AND node, what we get is 10 nodes. And again, let's see that what 10 nodes these are, right? So again, so these are the 10 nodes, right? So we had 3 nodes, 6 nodes, 7 nodes from before. And now we have 3 new nodes coming from the F, right? So if you remember our BDD or our COBDD for that one, it had basically 1 node and then it branched to 2 nodes and that merged to 1 node and then 1 node and 1, right? So that's the structure we have here. It's kind of slanted, which might make it a little bit hard to read because of all the other things here. But as you can see, it's sharing these 2 nodes with the XY1 completely, right? And we're only, I mean, if we had just had this function, we would have needed 6 nodes for it, but we only need 3 new nodes because of all the sharing that is going on. And again, we notice that, like, because we have referenced everything correctly, that nothing has been deleted and all of the references are fine, right? So for now, the things that you have seen in previous code examples as well. So does anyone have any questions up until now? Yes, no?
The OXC and OXB,
Yeah.
like, are they same?
No, they're not the same, right? So their OXC is going into OXB via. So okay, basically, so you have this solid edge and a double dotted edge going from OXC to OXB, right? So that basically means what? So you're saying that if OXC is decided based on x0, right? So if that is true, then whatever the value of OXB is, output that. But if x0 is false, then this is a dotted edge, which means a complemented 0R, right? So if x0 is false, that's basically saying that if x0 is false, then output the complement of whatever OXB is, right? So it's not exactly the same as, okay, you have two. Yeah.
It's the complemented edge,
Yeah. So the dotted edge is complement. In fact, in this diagram, I think all the dotted edges are dotted and not dashed, and they're all complemented edges. right? So
Yeah, I
dashed
got
is
confused with the
uncomplemented.
dashed one. Yeah.
Yeah. So any other questions? So okay, I mean, it is just saying this, that like if it is a sort of a complicated diagram and it might take some time to digest it, which since I have to finish within half an hour, I recommend that you go over this code again once outside of this class and see that you're following the construction of the BDD for these examples, including all of these, extraneous things and where things are being shared and stuff like that. And that's actually a really good exercise to follow on your own. If you have some questions or doubts regarding that, ask right now. Otherwise, I'll have to sort of move on to deleting nodes, because that is also kind of important, right? Any doubts? Okay. So yeah, so this until this now, this is just a more complicated example of the same construction that we had in the previous two things. Now in this code, what we do new is basically we start deleting things, right? So as we saw, this is a combined function constructed in print_stat that is basically give us this 10, right? So now we have, yeah. Hello, did anyone say something? Hello. Hello.
No, I don't think so.
Okay. Sorry. So yeah. So now we have this this whole BDD, and we see that there are some unnecessary functions here, right? So for example, to say our end goal was constructing f, then we see that this xy0 function is completely unnecessary. I mean, we needed it for the and, but once we have done the and, this is just we don't need this anymore, right? So it would make sense to want to delete this, correct? So that's what we try to do right now. So the way you delete something is essentially you really can't delete nodes on your own. All you can do is essentially just decrement the reference count of the node, right? So there is basically one function that CUDD gives to you to decrement the reference count of the node, and that is basically this CUDD iter deref BDD, right? So when you do this, it will decrement it will take a manager. Note that adding a reference did not take a manager, but deleting a reference does take a manager, and there's a reason for that, which I'll come to. So it'll take a manager, and it'll take the node that you want to delete a reference to, and it'll basically delete that reference, right? So when you delete a reference to the node, what happens is basically if say that was the last reference that was being held to that node, then if you delete that reference, the reference count of that node becomes 0. So then what you're telling CUDD is basically, okay, next time whenever you do garbage collection, delete this node, and it will delete this node very soon after you dereference it to like set the node's reference count to 0. It actually does garbage collection fairly often, and I think it doesn't even do it like in holes, but I mean it's very efficient about garbage collection and things like that, right? So there are a few methods that you have for dereferencing, right? So one is let's look at this. So why do we need this manager here? So as you see, the name of this method is iter deref BDD. So you see, let's look at this OXC function, OXC node over here. Say that you delete this reference you had from xy0 to OXC. So now OXC itself has 0 reference, right? Thing is, CUDD will go ahead and delete this, but that in one garbage collection it will only delete this, and it will then reduce the reference counts to the other node. So it will keep this OXB around because we haven't explicitly reduced the count of OXB, right? CUDD will therefore what we'll do is, okay, we'll say that, okay, OXC has a 0 count, but OXB has a non-zero count. So let's keep this around, right? And okay, let's imagine that there was no edge from y0 to OXB. So the OXB's count was 2. And then CUDD goes ahead and deletes the OXC node in the first garbage collection pass. Then OXB becomes 0. And so then CUDD has to do another garbage collection pass to delete OXB, correct? So essentially what we wanted to, so if we did not have any reference from the x0 to OXB, what we would want to do is to delete OXC and OXB at the same time, right? We would want to mark both of them for deletion and do it in the same garbage collection pass. And that will be much more efficient than doing it piecemeal like this, right? But if you only deleted the reference of OXC, then that's what would have happened, right? So that's why we call this function, there is another function called just dref, which is basically the complement of ref, and that doesn't take in the manager. And what that will do is it will only delete the reference of the node that you're passing in, right? So that function basically looks like this. Sorry, this. So that function would look like.
Diganta.
Yeah.
So
Yeah.
I'm stepping out.
Okay.
So for after at 12:30, you can stop the recording. Okay. So you will have a copy of the recording. I'll come and stop the live stream too, so I'll have a backup thing.
Okay.
But I won't be here when you think. So you end at 12:30. Okay.
Okay. Okay. Sure. Yeah. Yeah. I'll end in like 5-6 minutes. I don't have, too much. So yeah, so we could have done it this way. So what that would have done is it would have just deleted this reference, but it would have kept around these two references, right? And we don't want that, is what I'm saying. So that's why we, instead of using this particular direct function, I mean, there might be some use cases for this direct function, but I've myself personally never found one. What I usually use is just this iter direct BDD function, and that will basically delete the reference to your node, and it will delete all the reference going out of that node, and it will recursively delete all the reference going out of the children nodes if they get if we have deleted all the reference going into them from our parent nodes and so on. So in this case, it will delete this reference, it will delete these two reference, and say if this reference was not there, the why not to, okay, so it will delete the reference from x1, it will delete the two reference from OXC to OXB, and if the why not to OXB to 1, right? So it'll iteratively go ahead and delete. So okay, so we iteratively do this dereferencing for XY0, right? So let's see what happens after that. So once we delete XY0, I've written some things here, but that's okay. So XY0, we again do booking with our arrays, and then we dump the dot again. So, and then we print out statistics, right? So let's look at the dot and let's look at the statistics and see what's happening. So the statistics say that after we have deleted XY0, which is over here, we are now still have 4 variables, which is fine, but we now have 9 nodes, right? We delete 1 exactly, and that is fine, right? Because when we delete this OX0, this, or when we dereference this OX0, this one goes to, it will be fine. These two references get deleted, but since we do have the Y0 to OXB reference, right? While the XY0 to OXC and OXC to OXB references do get deleted, the Y0 to OXB reference remains, right? So OXB still has a reference count of 1, and that node stays behind. And then we end up only deleting XC from X0 to OXA and Y0 to OXB. The OXC node is no longer there. And now we have 9 nodes because we have 1 node less because of the OXC, right? Okay. So now let's delete Y0 as well, because we don't want any of these extra nodes at all, right? So let's delete Y0 and see what happens. So again, we do the same iter diref BDD. I'm at line 134 over here. So we do that. And then we again do some bookkeeping, and again, we print out the dots and out this, right? So the same iter diref BDD that we have to do every time we delete the node. So yeah, so now we have deleted Y0, and we again see that we have got rid of 1 node, which makes sense, right? When we delete Y0, we're basically deleting the reference from Y0 to OXB that sends OXB's reference count to 0, and we have deleted the OXB node, and that's what the dot also shows you. So OXB is not there, OXA is still remaining. Now let's in one pass, let's delete everything other than X. So we delete X0, right? So when we delete X0, the reference from X0 to OXA goes. OXA becomes 0 reference, like OXA's reference count goes to 0, so we delete OXA. So that means we lose 1 node, which is OXA. We delete X1 and Y1, right? So when we delete X1, we lose the reference from X1 to OXE. OXE becomes has reference count 0 now, so that gets deleted. That gets garbage collected. So OXA and OXE are gone. Then we delete Y1. So when we delete Y1, the reference from Y1 to OXF goes, but OXF already also has those references coming in from OX10. So that means OX10 get deleted. And then we delete XY1. So again, that deletes the reference from XY OX10, but again, OX10 has 2 references from OX14 and OX15. That means OX10 doesn't get deleted, right? The OX10 still has reference count of 2. So if we delete x0, y0, x1, y1 in this case, again, the code is in terms of code, we are actually saying dereference all of these, right? So when we dereference y1, x0, y1, x1, and xy1, then what we'll end up losing is just 2 nodes. And that's what the statistics tells us as well, right? So we delete everything but f is what we say here before printing the statistics. And we lose 2 nodes. So now we have 6 nodes. And if you look at the dot file, see, we have 6 nodes now. So all of these, all of the x0, x1, y1, xy1 functions get deleted in our bookkeeping. And we have gotten rid of oxa and oxe. So notice that other than oxa and oxe, all the other nodes are here, and they're just been printed straight instead of this slanted manner, right? So we have ox16, ox14, ox15, ox10, and oxf as we had previously, right? Right. So now let's add another expression. So now let's add not of y1. So we go here and we are adding not of y1. So to do that, again, we take in. So if you remember, we had sort of deleted the y1 node over here, right? Right. So we have done an iterative BDD on y1. So if you try to use this same y1 pointer, that might cause some issues. So instead, what we do is we create a new pointer to the y1 variable. And if you remember, the y1 variable's index was 3, right? So we get a pointer to the y1 variable's BDD by using this UBDDIFR. And we don't reference this pointer because we're treating this as temporary pointer to the y1 variable. So that this basically this reference to the y1 variable's node, which in this case is oxf, this reference never gets counted. But what we do then is we not this, and then we have a pointer that is pointing to the not of y1, and then we reference this, right? And again, we do some bookkeeping and print out the statistics. So now we have a pointer to the not of y1. Now, how many nodes do we have? So we go into here when we see that we are saying added not y1. So it seems that we have still 6 nodes, right? Because as you remember, this is COBDT. So not of y1 and the y1 oxf we have will be shared. And if you actually see the BDD, that's what's happening. So now we have f and we have not of y1, and there's just a dotted line coming from oxf. And so when we reference this not of y1, all that is basically doing is now incrementing the reference count of oxf. So the reference count of oxf is now 3. So now let's do something. Now let's delete f. So now what we do is we do iterative BDD of f. So what that will do is that will reduce the reference count of, that will basically delete the reference from f to ox16. ox16 becomes 0. So then delete all the reference from ox16 to x15 and 14. They become 0. The reference from ox15 to 1 becomes 0. And to f become, sorry, references get deleted, but oxf still has a reference from not of y1, right? So oxf will finally not get. So we end up and that's we know. So this basically take this is that while using COBDT, you sort of need to keep track of these reference counts, and that can be sort of something that you need to keep in the back of your mind and be careful about when you code, because this can lead to both dangling pointer issues and memory leakage issues. If you hold around, you don't have the reference counted, then you can get a dangling pointer. If you end up holding around reference, but you delete the pointer, but you don't reduce the reference count, you can end up with a memory leak and so on, right? If you're using C++, if you're using C, you just need to be really disciplined about this, about always making sure that whenever you're picking pointer to manage your reference counts accordingly. If you're using C++, then use ddNote pointer in a class where the constructor increases the reference count, the destructor reduces the reference count, right? So these are 2 ways of this, but basically you need to figure out and manage this properly. So yeah, so this is what all I had. Any questions? Sorry
Yeah.
for rushing a little at the end.
One comment I had was, did you discuss renaming variables? I mean, I know that there is, that is something that you need to do, is because, I mean, two BDDs that they may be implementing the same function, but if they have different variables, they're considered two distinct BDDs, okay? Because the variables are different. So if you have, a function in terms of x and another function in terms of x prime, technically they are two different BDDs because they are use two different variables. Sometimes you may need to rename those variables. Okay.
Yeah. Yeah.
And there are functions to do that, or I don't know if I guess how you may have to do it.
Yeah, so there's so CUDD package itself, which is basically why I wasn't mentioning this, because that's something that you need to figure out in your implementation side outside of CUDD. CUDD package itself doesn't let you in any case in any way rename variables, because for CUDD all a variable is just the index, right? So if you have a function in terms of say variable 0, 1, and 2, but you have the same function in terms of 0, let's say 3, 4, and 5, then there is no way of CUDD for CUDD to know that those are actually the same functions, that those need to be shared unless you create this new function in terms of 0, 1, and 2. So the way that I would suggest that you handle this is basically whenever you're creating this function, these functions just make sure that you create in terms of one common set of function variables, and then whenever you want to re-express this function in terms of new variables, just equate those variables over. So for example, if you have a function f,
doing it. Okay.
Yeah, so that's what I think I did when I did like the project as well. So
I mean, the reason I'm bringing this thing up, later, one of the things that you'll be repeatedly doing is, as you know, image computation. So we saw that in symbolic thing, the first instance of the thing was repeatedly doing image computation, which means that you will be applying, you'll be computing image over a tx, okay? And the t itself, the transition relation will be expressed as a relation between a bunch of, it'll be, you will be transforming one function in terms of the pre-variables into another function in terms of the post-variables, okay? So that is what you'll be doing. Sometimes that, there are various ways to do it, okay? One is to equate variables, or you keep two copies of t and then you get different things. And so you will encounter that. These are some technical issues that as you implement these fixed point, the first exercise that you will actually be doing is implementing the fixed point thing. Anyway, so we will talk more about in the when we meet again in the afternoon. I'll try to keep the today's class short, okay, and I won't go beyond things. So because you've had.
Sorry for taking a little longer.
No. I mean, they've also had. I forced them to take too many, impose too many sessions over the last few days, and therefore I'll go a little bit easy on things. So I'm sure you will have questions, okay, as you start implementing. Now, one thing that do you have some simple small exercise that you could actually have them do as the first exercise? I mean, I don't know. I mean, they could directly start doing, implementing the fixed point reachability analysis, okay? And then do it. Before that, if there is some small exercise where they can do image, okay, implement the image or something like that, okay, and then do repeated image as a step towards the thing. That is something that I would think. So take a transition relation and do a repeated image computation.
Okay. In fact, this will basically make apparent these issues that we are talking about, this variable renaming and all of these. I think if you try to do this with CUDD, this will you'll encounter these issues, and then it'll make you think about how to actually deal with them. So maybe take a transition.
So what I'm saying is to implement a program as an exercise. I'll make it very well defined. Implement a program which takes a BDD representing a function, and representing some set, okay, of states, and a transition relation, which is another formula, then computes the image of that set X under T SS prime, which is basically taking existential quantification. When I'm doing existential quantification, I'll show you, I'll show what that function is, and that you can take as the first exercise to play, because that will be the first, you can also reuse them in your CTL model checking. Okay, try to do that, and then you can repeatedly try and apply that image computation. Okay. Yeah. So I will. If there are no questions, then I will end it here, and I'll see you.
I would really recommend everyone going to the docs once at some point. Yeah. But yeah, that's all I have. So I'll stop.